Hi there, class. Welcome to Lesson 9-1, Adding and Subtracting Rational Expressions. This is Mrs. Brunk. And our essential question today is, how do you add and subtract rational expressions? So we just got done talking about graphs of rational expressions, and we even looked at writing some rational expressions to model some real-life situations. And so today we're going to shift our focus now to doing some operations with rational expressions, and we're going to start off with adding and subtracting. Now I'd like to go and look at a related example from way back in your math background, and that's when we added simple numeric fractions. So let's say you're asked to add these two fractions, 1/3 and 1/4. Now you probably remember that in order to add and subtract fractions, you must have a common denominator. And so when we're looking for a common denominator, and we can see that clearly they're not common here, what we're looking for is the least common multiple. So in other words, we're looking for the smallest number that is a multiple of both 3 and 4, and then what we're going to try to do is change both of the denominators of these fractions to that number by multiplying by whatever factor we need to get that denominator. So for instance, with 3 and 4, the least common multiple would be 12, and so in order to get 12 out of the 3, I'd have to multiply by 4. And in order to get that out of the 4, I'd have to multiply by 3. And so when we do that, though, that is changing the balance of that fraction unless we do the exact same thing to the numerator. So to the one on the top of the 1/3, I also have to multiply by 4, and as well as multiplying the top of the 1/4 by a 3. So essentially what we're doing is just multiplying by 1, and by multiplying by 1, we are not really changing our fractions at all. And so what that's going to do is turn this one into 4/12. It's going to turn the other one into 3/12. And now we are able to then add them together by simply adding the numerators, which add up to 7, and the denominator will stay the same at 12. And then if it was possible to reduce, we would. But in this case, it's not possible. So we had to get a common denominator. So how's that going to work when we have rational expressions that have variables in it? So that's, of course, going to be a little more complicated. And so we're going to start off by just taking a look at how we could write an expression that had an equivalent denominator. So we're going to start off with example A, rewrite the expression as indicated. So we're starting off with this expression, 3x over x plus 3. But if we wanted to write an equivalent expression to this, but have its denominator be instead x plus 3 times x plus 5, so what we would need to do is we need to change that denominator and give it another factor other than the x plus 3. So we would want to multiply by an x plus 5, and we know that if we do that, to keep the fraction equivalent, we have to do the exact same thing to the top. And again, that's really what it looks like when we're trying to change a denominator to get a common denominator. So this will kind of be the process that we'll use to get a common denominator when we're going to be adding and subtracting these expressions. So I'd go ahead and multiply the top and the bottom by x plus 5, and that would turn the top into 3x squared plus 15x. And then if I wanted to go ahead and multiply the bottom out, although most of the time with these operations we're going to do we won't, we could use FOIL. But instead I'm just going to leave it in this factored form, x plus 3 times x plus 5. And so we've written it with this new denominator. Now in our next example, we're going to learn how to simplify the expression. So it looks pretty complicated, the expression we have right now. We've got a trinomial on the top, a trinomial on the bottom, as well as a binomial. And so for me, the first thing I'd want to do is see if maybe there's some common factors that I could reduce the fractions by. Just like if we had, say, a fraction like 10/20, we'd see, well, do they have something in common that we could, reduce the top and the bottom by? Well, we want to do the same thing, but now it's not as easy to see the factors in these. So we want to put them in factored form. I'm going to go ahead and take the x squared plus 5x plus 6, and I'm going to factor that down into its binomials, and they both would start with x, and they'd end with numbers that multiply to 6 and add to 5, which would be a positive 3 and a positive 2. On the denominator, I'm going to take the trinomial and factor that, and then I also already have an x plus 3. So the x squared plus 3x plus 2 can factor into an x plus 2 and an x plus 1. And now we can see that we have lots of things that are common on the numerator and the denominator. And so just like that 10/20ths, the numerator and denominator both had a factor of 10, and we could cancel that out of the top and the bottom. We can do the same thing here with this x plus 3. Those can cancel. With the x plus 2, those can cancel. And now what remains on the top, now that everything has canceled out, because what we're really doing is dividing, is really just a 1 left. And so I'm left with this expression, 1 over x plus 1. And that would be in the most reduced form. So that's also going to help us as we're trying to reduce, once we are able to do these operations with these rational expressions, but then how we can then reduce them into lowest terms. So we're going to go ahead and give you an opportunity to try these on your own. An example like each one of the two that we've gone over. So in the first one, number 2, we're going to write 5 over 5x minus 25 as an equivalent expression with a denominator of x minus 5 and x plus 1. And actually I'm going to get you started on that one. And then in the second one to simplify. So do as much factoring and reducing as you can possibly do. I'll go ahead and get you started on number 2 because in order to get this with the denominator of x minus 5 and x plus 1, because right now it doesn't have either one of those factors as a denominator. But what we could do is we could take that 5x minus 25, we could factor out the 5, factor out the 5, giving us 5 times x minus 5. And then because we actually have a 5 on the top and on the bottom, we could cancel that 5 out of the top and the bottom, leaving me with 1 over x minus 5. And that should make things much easier for you as you try to get that denominator now of x minus 5x plus 1. So go ahead and continue that one, and then you can tune back in to check the final answer. And then with number 3, I'm just going to give you a couple little hints on that as well. Actually, that one looks like that one's fairly complicated. So I'm going to have you go ahead and give it a try, but when you tune back in, I'll actually go through and show all the steps for simplifying that one for you. So go ahead and pause the video now and try the examples. All right, so thanks for giving those two examples a try, those problems a try. So I've listed the answer for number 2, because again, I kind of got you halfway there. But number 3, I thought I'd kind of walk you through the rest of it. So what I did, and hopefully you were able to do this as well, maybe you got all the way to the simplified version, which actually, surprisingly, this is going to boil all the way down to just 1 over x by the time we're done. So if you got all that way and that's what you got, that's kudos to you. That's awesome. But anyway, so what I did was took each one of these binomials and tried to simplify them where I could. So for instance, the x plus x cubed on the top, I just factored out an x. On the bottom, I actually factored out an x squared out of both of those terms. And then I actually saw that this 1 minus x to the 4th power, I actually could break that down. That's a difference of 2 squares. Oops, didn't mean to start it like that. And I could factor that as 1 minus x squared and 1 plus x squared, because again, that's difference of squares. So now that cancels out with quite a bit of the stuff in the top. I know I'm going to get these to cancel. So I've got a 1 plus x squared, which is right there, a 1 minus x squared, which is right there. And then finally, I can see that there's an x left on the top and an x squared. That's all that's really left. And so I can factor that x out of the top, leaving me with 1, and take an x out of the bottom, leave me with x. And that's where this 1 over x comes from. So there's quite a bit of simplifying on that one. Let's go ahead and turn the page and continue looking at adding and subtracting rational expressions. So our next example is going to be How do we identify the LCD of two rational expressions? So the least common denominator. And so we're going to look at that in this next example. So given two or more rational expressions, the least common denominator, or the LCD, is found by factoring each denominator and finding the least common multiple of the factors. So just like we found the least common multiple of 3 and 4 in order to make fractions with the same denominator, so we could add the ones in that introductory example, we're going to look at two rational expressions that have polynomials in their denominators, and we're going to look to see if we can find the least common multiple of those polynomials so that we can get a common denominator. So basically these are the two steps to find the LCD of rational expressions. We're going to factor each denominator completely and write any repeated factors as powers. We're going to list the different factors. If the denominators have common factors, use the highest power of each common factor. So these are our steps we're going to take. And so let's take a look at an example. So example A says that the first expression is negative 2 over 3x minus 15, and the second one is 6x over 4x plus 28, and we're trying to find an LCD, or least common denominator, for these rational expressions. Now, they haven't asked us to actually add or subtract them yet, but just kind of working on doing that. So again, first step is to see if there's any factoring we can do on those denominators. And I can see that I could take a 3 out of this denominator, and that'll leave me with 3 times x minus 5. And then out of the second one, that denominator, I could take a 4. So I could take 4 out of 4x, leaving me with x, and out of 28, leaving me with 7. And so right now, I see there's really nothing they have in common. I see a 3 and a 4, which was kind of good that I used that introductory example earlier, because we know what the least common multiple of 3 and 4 are. So we could start off by saying, well, we've got to make that denominator have a number that both 3 and 4 will divide into, so that's going to be 12. Okay. But then this fraction has an x minus 5, so it would also have to include that denominator. And this one has an x plus 7. So if I were able to get a denominator of 12 times x minus 5 times x plus 7 for each of those, then I would be able to put those together and actually add them. And just to kind of show you how we would do that, for instance, if I wanted to do that to this the second expression here, I could multiply by a 3, and then that would turn that 4 into 12, and then I could also multiply by the x minus 5, which would mean on the top I'd also have to multiply by a 3 and an x minus 5. And then if I wanted to do the same thing with the other expression, I would have to multiply the top and the bottom instead by, well, a 4, and then also an x plus 7, and again, then the top I would also have to multiply by that 4, and that x plus 7. Now, typically what I do when I'm actually getting these common denominators is I really, on the bottom, don't do a whole lot of cleaning that up. Like, I don't do a lot of that expanding out. I wouldn't do the FOIL or anything. I would just multiply the 3 and the 4, but then I would leave those binomial expressions separate. But on the numerator, because remember what we have to do is actually add those numerators together, we would want to go ahead and multiply those all out using our distributive property or FOIL or whatever is necessary, so that we would get them in expanded form that we can then put like terms together. So that's for another example, because we're not quite there yet where we're actually going to add, but that's what would be involved, is finding this LCM. So that's our practice in finding an least common denominator, or a least common multiple, in other words. Okay, so let's see if we can figure out the LCD, least common denominator, for example B. Well, we've got some factoring to do in those denominators. The first one, I can factor into two binomials that both start with x. They have to end with two numbers that multiply to positive 24 and add to negative 11. So factors that come to my mind are 8 and 3, and if they were both negative, they would fit the bill. They'd multiply to positive 24 and add to negative 11. So then looking at the other denominator, factoring it, I would get an x minus 3 and an x minus 3. So actually, that's got two x minus 3's. So they do have something in common. I mean, they have a common x minus 3. So I would only really need to include that just one time. That's that common one. So when I figure out this least common denominator, I need to have an x minus 3. But then, so that takes care of these. But then there's another x minus 3. So this would have to have another x minus 3 in that common denominator. And it would also have to have this x minus 8 that the other one does.
So that kind of comes back to this step 2 where it said to use the highest power of each common
factor. So that highest power came from this one, which really could have been written as x minus, that one right there, that could have been written as x minus 3 squared. And so that's why we needed to include two of them in our least common multiple. So I'm going to go ahead and have you pause the video now, and let's do the U-turn problems. And we'll have you go ahead and tune back in and check your answer. So go ahead and pause the video now. Give number 5 and 6 a try, looking only for the LCD. Again, we're not really doing any operations with these, and we're not really getting the fractions in that form. We're just kind of identifying what the least common denominator or the least common multiple would have been. So go ahead and pause the video now.
All right, so thanks for giving those a try. Here are your answers for number 5 and number 6. And be sure to make a note if there's anything that you see that you're struggling with. Let's go ahead and turn the page. So finally we've gotten to the point in the lesson we are actually going to add and or subtract rational expressions. And so now we got to kind of put it all together. So again, step 1 is really to evaluate maybe you do have common denominators. Sometimes you'll have the denominators that are the same and you can go right ahead and do the adding or the subtracting.
But in this case, excuse me, in either one of these expressions,
you don't have a common denominator. So we're going to go ahead and see if we can find that common denominator. And then once we get a common denominator, we'll go ahead and add the numerators or denominators. Well, in this case, this is adding. But in the second example, they want us to subtract. So let's go ahead and first see what the common denominator would be. So looking at the denominators, only this one really needs to be factored. And when I factor out, I have an x times x plus 1. And so I can see that the other one does have an x, but it has actually an x squared. And so that means that when I'm kind of figuring out that common denominator, and I think my LCM, oops, it's going to have an x squared, because again, we always take the higher of the power, so that's got a squared, and whereas this one's just to the first power. And then we also have to make sure that the terms also have an x plus 1. So whatever they're lacking, we're going to make sure we change those so that those denominators have those factors, and then we'll be able to put them together. So let's take a look at changing this first denominator. And so I can see that it's got the x squared. It's only missing an x plus 1. So I'm going to go ahead and multiply the top and the bottom by an x plus 1. Which again is really just like multiplying by 1, so that's why I'm not really changing the fraction. And then the second one, second expression is missing, well, it's got an x, but it's missing an x and then an x plus 1. So it needs another x on here. So I'm going to multiply the top and the bottom by an x. And so that's going to turn my denominators for both of them into x squared times x plus 1, which is, of course, that least common denominator. But now I've got to see what those numerators turn out to be, so I can then simplify, put all that common factors and things together. And so the second expression is really easy to simplify. It was just x squared times x. That makes it an x cubed. But this first expression is much more complicated because there's all kinds of things going on here. And I'm going to have to distribute a binomial and a trinomial. So let's see, I have x times x squared, that's x cubed. I have, let me see if I can fix this up. So then I have the x, say the x times the x squared, the x times the 4x, which makes 4x squared, the x times the 2, which is 2x, and then take the 1 and distribute it through. 1 times x squared is x squared, 1 times 4x is 4x, and 1 times 2 is 2. And now I'm going to go ahead and now that I have a common denominator, I'm going to add the numerators, but there's really just like terms here and here in the two separate expressions. And then within this expression itself, we have some x squared terms we want to put together. We've got some x terms we can put together, and we'll simplify that all into one expression. So I have an x squared and an x squared, that's 2x squared. I have an x to the 4x to the second and an x to the second, which is 5x squared. So those are all taken care of. That's done, that's done, that's done, that's done. I put the x terms together, that's 6x. Those are done, and then plus 2. And then, of course, my denominator is that common denominator, x squared times x plus 1. And so there's my final answer. 2x squared. Oops, I'm sorry. I just noticed that. I'm so glad I went to read through that again because I see that that's supposed to be a 2x cubed, not an x squared. Excuse me. That's an x cubed. 2x cubed plus 5x squared plus 6x plus 2 all over x squared times x plus 1. Now, a lot of times students will say, do you have to distribute that denominator through that x squared times x plus 1? And the reason why we don't is because just like when we saw when we were graphing these rational functions, it's really important to be able to see the denominator in factored form, because what it does is helps us identify the places where the function or the expression in this case are undefined. And that's actually one of the things that they asked us to do here, was to give the excluded values. And so we can tell right away that the two values that x cannot have is we know that x cannot be 0, and we also know that x cannot be -1. And so those are excluded values. Those would actually be where either holes or asymptotes would lie. But they wanted us to identify those as well. So let's take a look at example B then. So this time they want us to subtract. But as far as the setup, the process to get this started is going to be exactly the same. We want to see what would be the common denominator. And so in order to do that, we're going to have to factor the denominator. So I can see here that I have in a denominator I could take out an x, and that's going to make that x times x minus 5. And in the second one, I have an x squared. Now sometimes when I'm doing this, I might notice that something in the numerator will cancel with something in the denominator. Like you can see that in this first fraction, I mean, I could take an x here off that bottom and reduce this one on the top to just 2x. But in this case, because I can see that the other denominator actually has an x squared, that's really not going to help in that case, because I'm going to have to then turn around and make sure that the denominator has an x squared anyway. So I know that what this second one is missing, it's missing an x minus 5. So like my LCM, it's going to have an x minus 5 in it. But then it also is going to have this x squared that the second one has, that the first one has on x. But if we could make it into an x squared, that would be our denominator. So to make this first expression have that LCM as its denominator, it's missing an x, so it needs one more x. So I'm going to go ahead and multiply both the top and the bottom by an x. So I'm going to multiply top and bottom by x over x. And so that is going to turn that numerator into a 2x cubed. And it's going to make that denominator x squared times x minus 5. Now in the second expression, this one is missing an x minus 5. So to make this denominator be x squared times x minus 5, I'm going to multiply it by an x minus 5. But that means I'm also going to have to multiply the top by an x minus 5.
And so that means, again, I'm going to be multiplying a trinomial and a binomial. But now this time I'm going to be subtracting. So what I'm going to do is go ahead and figure out what that numerator is first, and then I'll worry about the subtraction. So you go ahead and distribute that through. So first I'm going to take the x and I'm going to distribute it through. So that's going to give me x cubed plus 3x squared minus 4x. And I'm going to take that negative 5 and distribute that through. So negative 5 times x squared is minus 5x squared. Then minus 5 and multiply it by the 3x, that makes minus 15x. And then the minus 5 times the minus 4 makes plus 20. We'll go ahead and clean all that up first before we worry about, again, subtracting. We'll do that at the very end. We'll do the actual subtracting, but let me just clean up that numerator. So if I put my like terms together, if I don't want to rewrite the whole thing, I think I'll just kind of write just the top. So let's see, there's only just the 1x cubed, so that's x to the third. That's done. I've got 3x squared and minus 5x squared. That's minus 2x squared. So those are done. I've got a minus 4x and a minus 15x. That makes minus 19x. And then finally I have the plus 20. Now here's how I'm going to take care of that subtraction, because again I'm subtracting, and so all I'm going to do to change this into addition is change this to an addition sign, and everything after it's going to change sign. So that was positive, it became negative. This is negative, it became positive. This is negative, it becomes positive, and this now becomes negative because it was positive. And now I can think about putting my like terms together with that denominator of x squared times x minus 5. So putting like terms together, let's see, there's a 2x cubed and a minus x cubed. That makes just x cubed. So again, I'm going to put this one and this one together. And then the x squared, so there's just the plus 2x squared. There's the plus 19x. And of course there's the minus 20. Now, it is pretty common practice for you to, check to make sure this is not maybe reducible. And so you want to always check that numerator and see, hey, can I factor that at all? Is this like a factor by grouping situation? And in this case, I can tell clearly it's not. But if it were able to be factored, then there might be something then that would reduce in the denominator. So we always want to take a look at it and see if that's possible. So that's our final difference between those two. And then we also want to make sure we say what values x cannot have. And so we can see here, looking at that denominator again, I can tell that x cannot equal 0 and x cannot also equal 5. Now for the your turn, the you try questions, they give you as the directions to both add and subtract these expressions. And so I'm going to go ahead and adjust the instructions, and I'm going to just have you on number 7, I'm going to ask you to add them, and then for number 8 I'll have you subtract. Just so that's a lot to do if you have to add and subtract both. And so we'll just go ahead and add on number 7 and subtract on number 8. And I'm going to go ahead and have you pause the video and give them a try. You can tune back in and I'll show the final answers, and you can make a note if you need any help that when we see each other in class you can ask about. One thing I want to real quick give you a heads up on, because on number 7 you might take a look at that first expression and say, well, that doesn't even have a denominator. Well, remember, if it doesn't really have a denominator, its denominator is actually 1. And that actually makes it a little easier because you can just use the other denominator as the LCM. So go ahead and pause the video now. Add the two expressions after you get a common denominator in number 7. Subtract the two expressions in number 8. Pause the video now. All right, so go ahead and check your answers here, and we're going to call this a day because the final examples are going to be our word problems, our application problems, and so we're going to go ahead and talk about those when we see each other in class. And so again, make note on any of these things that you might be struggling on, anything you want clarification on, and we'll be sure to talk about those things when I see you in class.